Here is a simple example, geometric series. We take 1 plus z squared plus c plus off to infinity. Now a partial sum Sn, that stops at nth power. We have a relation. So if I multiply partial sum by Zn, then it starts with Zn and goes to Zn plus 1. So we have a mismatch in the first term, that's 1. And then we have an extra term at the end. From that it follows that Sn for z magnitude smaller than 1 z to the n goes to 0. So this is going to be a convergent sequence. And for z larger than 1, Cn is going off to infinity. So that's divergent. But for z smaller than 1, we have now that the whole series, which is n to infinity, is 1 minus c and that's our usual geometric series. Now here is a puzzling little fact. If you consider function 1 plus z, no singularity, at I equals 1. So what's going on? I mean, it looks just like this one, it just has alternating signs. That's a series looking up there, it's just 1 minus c plus c squared minus c plus. So how come that series is okay? Well, as you'll see eventually, what matters is that there is a singularity someplace in the complex plane. So this one has singularity at z plus minus I. So they actually have the same convergence properties as far as complex series are concerned. So this little example of a geometric series showed us that not only polynomials, rational polynomials, but also infinite series can be holomorphic functions. And that brings us to our dear old friend, the exponential. Now we're not surprised to see that function here because remember, morally, z is really a number in 2 dimensions. And exponentiation of such numbers in a plane has to do by 2 matrices, and we found out that there was no problem in defining exponential over later. Now the wonderful thing about exponentials is they have infinite radius. In the example we just looked at, geometric series, the radius of convergence was 1. But for exponentials, they define every place there is no singularity, they're beautiful holomorphic functions. So that is called an entire function, a function that has no divergence any place in a complex frame. It's convergent every place. They're rare, they're not so easy. If you have them, they're magical, but they're rare. Exponential obeys addition formula, which is not obvious if you think of them as two-dimensional functions, but it has to do with the imaginary number really being a 2x2 matrix, and if there's only one such matrix, it commutes with itself, and that's why you can write this is a product of two functions with all the commutators which could have showed up in this exponential. They all vanish. Now, just looking at the power series expansion, you can verify that TDC of exponential is exponential. If C is real, this is just the ordinary exponential. If Z equals IY, pure imaginary, then the series splits up in a natural way because I squared is -1. Odd and even powers will behave differently. So you can split it into even powers, in which case this is going to be plus -1. I squared is -1, I to the 4th power is +1, plus odd powers. In that case you get plus minus I, depending whether it's a first power, third power, and if you split it into the two sums, if you write it as 1 minus next power plus the 4th power, all the even powers, and times I, first power minus third power, 5th power, you realize that the first expansion is simply a cosine y plus, and the second series is just a sine y. So this is, the amazing insight of Euler, a young Euler in 1740. And it leads to this totally remarkable thing that, e to the I pi equals -1, one of those totally crazy formulas in which natural numbers, pi, basis of exponentials, natural exponentials. This is a totally crazy formula. If you take a basis of natural logarithm, which is some weird number, you raise it to I, which is imaginary, and God knows what imaginary number means, multiply by pi, which is half of circumference of a circle, you get -1. It must have been totally astonishing when Euler found this. So, Euler says that if I take an exponential, its real part is the ordinary cosine, the geometrical thing. Now, just as a pure algebra and this weird number I in front, this would be very strange, but we have visualization in Gauss plane, so it's two-dimensional vector, I is rotation by 90 degrees, this is a real and imaginary part, everything is cool. Out of it come all kinds of handling formulas, like cosine of theta is 1/2 plus the complex conjugate, and sine of theta equals 1/2i minus complex conjugate. Our complex number, which is r cosine theta plus I, sine theta from real and imaginary representation in two-dimensional plane has a compact representation which is r positive number modulus times r beta. And now the multiplication rule is totally obvious because we already know that we are allowed to add up exponents. Roots are simple. Various identities are very simple. For example, is 1/4 e to the I theta plus to the minus I theta square plus 1/2I square. Same thing as minus. So there is a minus and a bunch of term cancels. I will not bore you with it. But we get 1. Hyperbolic functions are also very simple. We can define them by hyperbolic functions defined by analogy, except now we have real rather than imaginary exponents. Theta equal 1/2 e to the theta plus e to the minus theta. So sum of two exponentials. And sinh, hyperbolic version of sine, is same, but it is a minus sign, cos r theta. So cosine of imaginary. And you can think of this guy as minus I sine I theta. So hyperbolic functions and trigonometric functions are just imaginary cousins of each other. And you get nice identities such as the cos square of theta minus sine square of theta equals 1. Note, when you look at cosines of theta, it's no longer true that they are bounded by plus or minus 1 as they are for sines and cosines. This now can go any place from 0. And that will be one thing we will learn whenever we complexify a function. Even if we had some very nice bounds on a real line for its real values up in a complex frame, we can do weird stuff. Single valued function takes z, single point in a complex plane corresponding to z gets mapped to a single point in a function plane corresponding to w. Multi-valued function can take z into many, maybe even infinity points. Holomorphic means differentiable in a neighborhood, open neighborhood of the entire function means holomorphic over a whole complex plane. There are two kinds of points at which holomorphic function has a finite value, or it's singular if the function has infinite value. We saw that exponential is a beautiful function, nice and smooth, entire, defined every place. So what's a logarithm? It's a function that if I exponentiate a logarithm of z, I should get z back. It's an inverse of the logarithm. Let's say that logarithm of z is u plus I b, and z itself is x plus I y, or more usefully, e to the I theta magnitude in the complex phase. From here, we have e to the u plus I, just an ordinary exponential, e to the I, that's pure phase. So taking modulus implies that e to the u equals r, so that's the real part, e to the I theta. So this is no big deal. Exponential or real number is a real number. But this one now we have to remember that everything is defined modulo 2 pi. And this is so we find that a logarithm, real number u is a logarithm of real number r, but e is theta plus 2 pi k, where k is 0, or plus minus 1, or plus minus 2, or plus minus infinity. Any phase is allowed. One exponential corresponds to actually infinitely many points in a complex plane. So on the left hand side we have a z-plane, and we have z1, and let's draw a unit circle here. This is 1, r, 1, so I draw the circle. I want this to be inside the circle. So what I mean is that z1 has modulus smaller than 1, and z2 has modulus larger than 2. So now let's look at w equals logarithm of z-plane. And now what happens, this guy gets mapped, it's smaller than 1, so it gets mapped into negative number, logarithm of small numbers. So that's the fate of magnitude of this thing. Well, this guy gets mapped someplace here. But then we are allowed to multiply this by imaginary number 2 pi k, a number here which has a phase k equals 1, number here which has a phase equals k, k is minus 1. So there are infinitely many of these guys. This guy z2 can have argument 0 or 2 pi 1. A logarithm takes infinitely many values. So logarithm is really a multi-function. For example, root takes 2 values, there are 2 numbers squared that give me a given z. But logarithm has actually infinitely many values. So this is inconvenient to have function that has infinitely many values. So one thing is to define principal part, nothing to do with your ethics, but the most important part, which is denoted by capital L. So ln of z is defined to be the sensible logarithm of its magnitude, but you take theta that's only in the interval plus to minus pi. So in one rotation you pick a point, which if it's minus pi, that's in interval, and plus pi is not in interval because it's identified, so it's open at the right hand and closed at the left hand. That's sensible, but you pay a price, and that is that you get the discontinuity. So consider taking logarithm of z, varying it in such a way that its angle theta approaches pi from below. So you're at this end of the interval. So you increase theta until you're epsilon away from the edge. You can also vary z in such a way that you decrease theta until you are at minus pi, almost, so slightly less than minus pi. And if you look at the limit of plus pi and minus pi, well, if you take the same epsilon as you approach the limit, you either get a positive end of the interval or negative end of the interval. So what has happened is that the phase of principal part, by this definition, if you move in the z-plane as you approach angle plus pi, and you compare it to the angle minus pi, the principal part jumps by 2 pi. Very inconvenient. What really happens for the logarithm itself, that the phase just spirals and keeps increasing monotonically forever in a continuous way. But the principal part makes it look like it jumps, and you'll run into that often.